Hello, this is Professor Stephen Neshiba, and I'm here to help you out with a computational lab on Introduction to Molecular Orbitals. The idea of this computational lab is to familiarize you with molecular orbitals and some aspects of molecular orbital energy diagrams. So our first task is down here is to figure out is to enter in your notebook some of the characteristics of the bond between two hydrogen atoms. And for that purpose, I have, let's see, we have table 8.2 in your text. And there's HH, that's the bond length is 75 picometers. The bond energy is 436 kilojoules per mole. Now I've set up an Excel sheet that does this. And how did I get this 75? Well, as you can see, I took 75 picometers, divided it by 100, and that gives me the bond length in angstroms, and then I just entered that number there, 436. So let's see, the next piece of this is to get the bond length and strength characteristics of BH3 NH3. So I referenced, in the handout, I pointed you to this online article by Barron, and where he lists these bond lengths and bond strengths. That's fine. You could also have used the values that you got for the bond length and bond strength last week. I just thought I'd show you this one as well. So as you can see, the bond length is already in angstroms. The bond strength is in kcals per mole. Now let's go back to this. So as you can see, I've just entered in that same bond length. And for the bond strength, what I needed to do is I said it's 31 kcals per mole, and the conversion is to multiply by 4.18, and that's what gives us 130 kilojoules per mole. Our next task on this is, let's go to Spartan, and there's the hydrogen atom, and you'll have to add this, of course. Now there's setup calculations, B3 lip equilibrium geometry, not charged, but notice that I've had to put one unpaired electron, and so there we go. I've submitted it, and now it's all done. Yours will take a little bit longer because mine was already calculated. Once you get to there, though, you go to this little icon up here for the energies, and I've already set this up to show it in mesh view. So there's what's called the HOMO. That's the 1s orbital, and here we have the 2s orbital, and you can see that it's different and bigger. All right, so that's the 1s and the 2s. And the point to note here is that that 1s orbital down here has an energy of minus 8.6. We'll come back to that. Now, how about H2? I'm going to do the same thing. Of course, you'll do the same calculations. B3 lip, neutral. Of course, in this case, you'll want no unpaired electrons. And there we go. And I'm done. And once again, we go up to that ladder there. Here's the lowest energy, and as you can see, let's see, that's minus 11.8 electron volts. And the next one up there is this other cool orbital, and that's at 2.7 electron volts. So our last thing that I want you to do on H2 is to build a molecular orbital diagram. And I've kind of started it here for you, just so you can kind of see what I want you to enter into your laboratory notebook or your computational notebook. You remember that the energy of the 1s orbital for the hydrogen atom was about minus 8.6 eV, so I put up a scale of EVs here, and there it is at minus 8.6, and so is the other hydrogen atom. And there was that molecular orbital at about minus 11.8, and you'll want to fill in what the energy, the antibonding s orbital for H2 was. And then we'll just carry on with this in class.